Hello and welcome to Lecture 15 for the course ECE 252B, Spring 2020. Continuing our discussion of computer arithmetic, we now move into part 5 of the textbook, which deals with real arithmetic, which means arithmetic on real numbers as opposed to integers that we have been dealing with so far, or fixed point numbers, which are essentially like integers in terms of arithmetic operations. So there are 4 chapters in this part. I'm going to cover these 4 chapters in 3 lectures. Today, in this lecture, we'll cover chapter 17, floating point representation. Next lecture, we deal with floating point operations. And the third lecture for this part will deal mostly with chapter 19, errors and error control, with a little bit from chapter 20 on precise and certifiable arithmetic. Okay, so this lecture deals with floating point representations. Floating points is basically a way of representing real numbers in computers, but it's by no means the only way. We'll see some other methods in the next in 2 lectures from this one, the lecture after the next one. But at least one other method, logarithmic number representation, we deal with today. So today we'll be exposed to floating point representations, which are the most popular way of dealing with real arithmetic in computers, but also a little bit about logarithmic number representation. So floating point numbers, as I mentioned, represent one way of dealing with real numbers in computers. Of course, real numbers, non-integers, in other words, can be represented as fixed point numbers. Fixed point numbers have a whole part W and a fractional part F, and a radix point, which is often implied, so it's not explicitly represented. So we may have, for example, a 32-bit format in which there are maybe 20 bits in the whole part and 12 bits in the fractional part. That's an example of a fixed point representation. Rational representations basically use 2 integers, p and q, to represent the ratio p over q. So some real numbers, such as 1/3, will have exact representations in this format. So P1, Q3 represents 1/3. So some basically rational numbers can have exact representations. Of course, if P and or Q become too large, then any fixed format will not be able to accommodate them. Floating point is the main format we'll deal with today, and logarithmic representation. Towards the end of the lecture, we'll see what it is and what advantages it can offer over floating point. Now, fixed point numbers, as I said, have a certain number of bits for the whole part and a certain number of bits for the fractional part. In this example format, I'm using 8 bits for each of those, 8 bits for the whole part, 8 bits for the fractional part. So this first number, x, is a fairly small number because the whole part is 0 and the fractional part is relatively small. The second number is fairly large because the whole part is fairly large given the range of the format, and the fractional part is 0. So basically, one can say that when you represent small numbers, the bits representing the whole part sort of go to waste for very small numbers. And when you represent large numbers, the fractional bits may go to waste, because if a number is large, we typically are not interested in a lot of fractional bit. This is sort of like when you deal with the state or a country budget. The numbers are huge. So often, not only we don't represent the cents in those numbers, we may not even represent dollars, a few dollars. So we talk about a budget of, let's say, $22 million for a particular activity. So notice that when you say 22 million, that's 22 followed by 6 zeros. Not only we don't have any cents in this number, but also the last 6 digits of this number are all zeros, because we don't care about small variations when the number is so large. Now, floating point numbers are represented with 3 components. Actually, 4 components if you count the sign. So there's a sign, plus or minus. There is a significand. Sometimes it's called mantissa. Mantissa is the older term for it. The modern term is significand with a D at the end. An exponent base B and an exponent E. So the 4 components are sign, significand, base, and exponent. The base is often implied and is not explicitly shown. So there are really 3 components that are shown: sign, significand, and exponent. And the number represents plus or minus is the sign. Excuse me. Then significand times base to the power exponent. So the 2 numbers up there, x and y, may have this representation. X is 1.001. This is a decimal number. It's not a binary number, even though there's only ones and zeros. Oh, sorry. It's a binary number. And most of the examples I'll give you in this chapter are decimal. This one, in fact, is binary. It's a 16-bit number. So 1.001, just slightly greater than 1, is the significand. 2 to the power minus 5. And the second number is 1.001 times 2 to the plus 7. Notice that the significand happens to be the same for these two. This is a very small number because the exponent is negative. This is a large number because the exponent is positive. So this sign is actually the number sign. The exponent itself is usually a sign number, and we need some way of representing the exponent's sign. We'll talk about that later. So a floating point number really has 2 signs: the sign of the number, the entire number, and the sign of the exponent, which is usually embedded in the exponent. It's part of the representation of the exponent. Okay, the common way of arranging the bits in a floating point number is shown here. This doesn't have to be the case, but historically, floating point numbers have always been represented in this way. The sign is the first bit from the left. Then the bits of exponent come next, and the bits of significand. Okay, so this is ordering. Sine, then standard sine encoding, plus is 0, minus is 1. The exponent is a sine integer, often represented in bias format. So instead of having a sign and magnitude or using 2's complement for the exponent, the common way of representing the exponent is to use a bias. In other words, add some positive number to all exponents so that the most negative exponent becomes 0. Okay, so basically the exponent becomes an unsigned number. And then we interpret that exponent. If it's a small unsigned number, then it's negative. We subtract the bias from it basically to see what actual exponent is being represented. So the range of the exponent goes from minus bias. So minus bias basically becomes 0, represented as 0, because we add bias to it. And 2 to the h minus 1 is the largest value you can represent in h bits. Minus bias is the most positive exponent. And then the significand is usually normalized so that the first bit of the significand is always 1. And because the first bit is always 1, we don't need to represent that, saving 1 bit. That's called the hidden bit. Okay, I just realized I haven't used the slideshow. Okay. So because this first bit of the significand is always 1, we can hide it, not show it, and by doing so we save 1 bit in the representation. Now this is basically a schematic diagram showing the distribution of floating point numbers over the real number line. Of course, there are infinitely many real numbers. Any finite representation system can only represent a finite number of alternatives. These tick marks basically show the values on the real number line that we actually represent. And those on the positive side, they go from min plus, the smallest positive number that we can represent, to max plus. So these tick marks, and the tick marks, as you notice, are closer to each other for smaller numbers, and they get progressively further from each other for larger numbers. This is actually a positive attribute for floating point representation, because as numbers get larger and larger, we don't need as much precision in the representation. So the fact that the tick marks get further from each other is not a drawback. It's actually a plus, because that allows us to represent a wider range. On the negative side, min minus is just a mirror image of that side. Min minus is the smallest, is a negative number with the smallest magnitude. Max minus, and again the numbers, the tick marks have greater spacing as we go towards numbers with larger magnitudes. Okay? Besides these, what we call ordinary or standard floating point numbers, there are special codes for plus or minus 0. For plus infinity, that's basically a number that is too large to be represented. It's a special marker. And minus infinity, a number that is too negative to be represented, as we use that marker to represent it. Okay, notice because we are requiring the first bit to be 1, 0 does not have a proper representation in this format because 0 will have a 0 significant, and a 0 significant does not have a leading 1, so it cannot be represented in that format. Therefore, we need special codes for 0, plus or minus 0, special codes for plus or minus infinity. Now, when a number gets too large, when it exceeds a max plus, we say we have overflow. So if you do some computation and you get a number in this range, we have encountered overflow. When a number is encountered in the course of computation that falls in this range, between negative max and negative infinity, well, it's tempting to call that underflow, but that's also overflow. The word underflow is reserved for these regions. When a number is encountered in the course of computation that is between 0 and min plus, or between 0 and min minus, so an actual real number that does not have a representation in this system, we have to basically have a special, we can round it, for example. If it's very close to min plus, then we may round it to min plus by committing a small amount of error. More often, however, when we encounter underflow, we flush the number to 0. Later we will talk about denormal numbers, but let's forget about that. There are no numbers representable in this gap. Therefore, we flush those values to 0, basically arguing that these numbers are very small, and therefore just representing them as 0 will not cause any trouble. Usually that's in fact the case, but there are situations. And in the chapter on errors and error control, we see that even such a small error can cause problems in computation. Okay, here is a brief history of floating point representations before and after the IEEE standard. Now, in the old days when I first started taking courses in computer architecture, we basically had to learn about different formats on different computers. Each manufacturer had its own floating point format in terms of the number of bits, the exponent encoding, the base, and so on. We had to learn about all of those. This created many problems because floating point computations could produce vastly different results when run on different computers. So you wrote a program that did floating point calculations, the exact same program, let's say in a high-level language such as Fortran. When you ran it on different machines, it produced vastly different results. Not just, varying in the last few bits, but sometimes completely different results because of the way errors accumulate in floating point computations. Again, we'll talk about errors later. Now there's this website, this URL, that has a very interesting table where you can sort of, if you're curious to see, all the different floating point formats that have ever existed, this table lists them. First IEEE standard for binary floating point arithmetic was adopted in 1985 after years of discussion. There was a lot of heated discussion. Basically, each manufacturer tried to sort of make sure that their format was adopted as standard. and there was a lot of fighting. Eventually, agreement was reached on a particular format, and that was officially adopted as a standard in 1985. So it's called IEEE 754, that's the standard number, dash 1985. The 1985 standard was continuously discussed, criticized, and clarified for a couple of decades. Okay, and then time came to, all standards, all IEEE standards are subject to revisions every decade or so. So after 2 decades, it was time to sort of revise and update the standard. And that effort bore fruit in 2008, where a revised standard was issued. So this is IEEE 754-2008. After another decade, discussions started for revising the standard. There were a lot of heated discussions as usual, and the standard was eventually finalized and adopted in 2019. So the latest version of this IEEE 754 standard is IEEE 754-2019, which is in effect today. So the IEEE floating point standard, the binary part of it, it also has a decimal part, has two main formats. These are basically the workhorses, what is used most often. The 32-bit or short format and the 64-bit or long format. Both formats have a sign bit at the left end. The short format has an 8-bit exponent with a bias of 127. So the exponent values go from minus 126 to 127. So minus 126 when biased by 127 gives you 1. So when the number 1 appears there, that's the most negative exponent. 127 plus 127 is 254. When 254 occurs there, that's the most positive exponent. You notice that two codes are missing here. 0 is not used, and 255 is not used. Those two extreme I'll show you in a minute. They're used to encode special values in this standard. Okay, so we have purposely left those two codes unused so that we can use them for encoding those special values, plus or minus 0, plus or minus infinity, and a few others. Then there are 23 bits for the fractional part of the significand, and there's a hidden one that is not shown. So the significand is always of the form 1 point something, and that something, 23 bits, is shown here. Okay, now the 64-bit format has a wider exponent field, 11 bits, with a bias 1023. The most negative exponent value is negative 1022, which is encoded as 1. Add the bias to it. And the most positive is 1023, which is encoded as 2026. Again, 0 and 2046. 2047 and 0 are not used. Again, there's a hidden one with 52 bits. So this format has both a wider range because the exponents can be larger, can represent larger numbers, and also smaller numbers, because with negative exponents you can represent very small numbers. And also more precision because there are more bits in the significand. So as I mentioned, the exponent encoding for the short IEEE format is such that the values -126 to +127 are encoded as numbers 1 through 254, or in hex as 01 to FE, 0 or 00 in hex, and 255 FF in hex. Those are special values, are used to represent special values. So those are ordinary. In the middle, you see the ordinary floating point numbers that are of the form 1.f times 2 to the e. The special code 0 in the exponent field is used if the significand is also 0, if the fractional part of the significand is also 0. So the exponent is 0 and the fraction is 0. That's the representation of plus or minus 0. This is the sign bit. So basically, plus or minus 0 is all zeros except for the sign bit, which can be 1 for -0. And if f is non-zero, then those are representations of subnormals. These used to be called denormals, but now the modern term is subnormals. And these numbers are 0.f times 2 to the minus 126. In other words, there's no hidden 1 anymore. Okay? So that special code, when it appears in the exponent field, means the exponent is still this, the most negative exponent, but the fractional part is a true fraction. There's no hidden 1 there. On the other end of the exponent range, if the exponent field contains 255, the all ones exponent, if the fraction is 0, if the significand is 0, we are representing plus or minus infinity. Again, plus or minus comes from the sign bit. And if the fractional part is non-zero, then we are representing what we call not a number, N-A-N, nan. Okay, we pronounce that nan. So nan is something that is not a number. So it's used as a special code whenever you do things that lead to a non-numerical result. So for example, one application would be when you divide by 0, it's a sort of an exception. Okay, so whenever you encounter the nan code for a number, means you can't be sure of the value of this number. It's a special code for undefined, you might say. Okay, so subnormals basically are numbers that fill the gap between this min and 0. So min is basically the smallest number that can be represented as an ordinary floating point number. So that smaller number will have basically the significand equal to 1, the fractional part 0, times 2 to the minus 126. So that's the smallest number. Now with subnormals, we can multiply this to the minus 126 by this fraction, and therefore we can have numbers in that gap Therefore, the effect of underflow is not as devastating as if you did not have these subnormals. Without subnormals, a value that fell over here had to be flushed to zero. Therefore, you would commit a fairly large error. And this error can be fairly large compared with the spacing that you have there. Whereas when you fill that gap with these subnormal numbers, then the error will be reduced. So you can represent quite a few values in that previously empty interval. Okay, when you divide an ordinary number is one of these, basically anything other than 0 or plus or minus infinity. It's called an ordinary number. When you divide it by plus infinity, you get plus or minus 0 depending on the sign of this ordinary number. Anything divided by infinity is 0 with the appropriate sign. When you multiply plus infinity by an ordinary number, again you get plus or minus infinity depending on the sign of this number. When you operate on a nan, an ordinary number, the result is nan. So undefined value added to some ordinary number, the result is undefined. These are all logically, basically, they make sense logically, they're intuitive. Okay, there are also extended format, and these are not part of the standard, but just suggestions that if you're dealing with single precision or short numbers, typically you may want to keep a wider format internally in the computer in order to control the errors. We'll talk about the errors in detail later. But for now, so when you add two floating point numbers, the result may be too large to be represented here. But on the other hand, that sum may enter into another floating point operation and be reduced subsequently. So it's a shame to basically lose that number because it's not representable. Whereas the final result, so a plus b plus c, when you do a plus b plus c, a plus b may not be representable. But if c is negative, a plus b plus c can be representable. So you keep intermediate results with wider range, more exponent bits, and more precision, okay, so that you can do these intermediate computations with as little error as possible. And then eventually you will round that to this format before storing the value in memory. So that's single extended. Similarly, we have a double extended format that has an even wider range than the double format, than the long format, and more precision than the long format. Okay, this table basically shows the IEEE 754 2019 formats, binary and decimal. I already told you about the 32 and 64, the most frequently used formats for binary floating point. Recently, the 16-bit format, because multimedia and other low precision applications are gaining ground, the 16-bit format is also becoming popular. Of course, this is not very precise because you have one sign bit, 5 exponent bits, that's 6 bits, and 10 fractional bits. Okay, it says 11 here because it counts the hidden 1 as well. Here they have the hidden 1 plus 23 bits. Here the hidden 1 plus 52 bits. There's also binary 128 for, for most scientific and engineering calculations. 64 bits is more than enough. But if you're doing certain computations, modeling and stuff where even higher precision and wider range is needed, you may want to use the 128. So this is called double precision or long. This is called quadruple precision. And then octuple precision for 256. These are defined because a standard has to be forward-looking. So maybe in future, just as 16-bit became popular recently, maybe 128 and 256 will also become popular in future. They're defined, okay? Then for decimal, there's the 32-bit format, 64-bit format, and 128-bit format. For decimal, it doesn't make sense to go to the 16-bit format. And so the base here is 10. There are 7 digits in the significand. Okay, so 7 decimal digits. Now a decimal digit can be encoded in 4 bits, although more compact representations are also available. But assuming that you use 4 bits, that's already 28 bits. Okay, it doesn't leave you much because you need a sign bit and 28 bits for this. That 29, that leaves you only 3 bits for the exponent. Okay, whereas the exponent bit is a little bit over 7 here. That's because those 7 decimal digits are encoded in more compact format than usually 4 bits per digit. Okay, I won't talk much about decimal format. I just take this opportunity to let you know that at one point everything in computers was binary. So when we did, for example, financial calculations, we represented numbers in binary. And for example, the cents figure, so if you had, say, $2.52, that 52 cents may not have an exact representation in binary. Therefore, you lost some precision. And these errors could add up and become significant. So you would get imprecise financial calculations. If you do financial calculations directly in decimal, then you don't lose any precision because you can represent numbers exactly in the decimal format. There are other domains where decimal arithmetic is becoming popular, so perhaps in future, of course, we deal with decimal numbers, and whenever we want to interpret output from a computer, we convert it to decimal view. So that conversion also causes errors in both directions, going from the input that is decimal to binary internal representation, and then going back from the binary internal representation to decimal output. So it would be nice if we could do everything in decimal from input to calculations to output, avoid the need for those conversions, and avoid the errors from those conversions. Now, up to a few years ago, decimal arithmetic was too expensive to be practical, but nowadays with very cheap hardware and with improved algorithms for dealing directly with decimal numbers, we can afford to do things directly in decimal, and therefore my expectation at least is that in future decimal floating point arithmetic will become much more popular than it is today. So as part of the decimal, as part of the uh, standard, the standard not only defines representation format, but also expectations or requirements for arithmetic. It says that the results of the 4 basic arithmetic operations, add, subtract, multiply, divide, as well as square rooting, which is now considered a basic arithmetic operation, must match those obtained if all intermediate computations were infinitely precise. In other words, adherence to the IEEE standard means you implement your ALU or whatever arithmetic unit you are implementing, arithmetic circuit you're implementing. It should yield a result that whose only error is the final rounding. In other words, if you compute the intermediate results with infinite precision, of course, infinitely precise computation is not practical. So what that means is that you have to emulate the effect of infinitely precise. In other words, ensure that your operations do not lose any precision. Okay, that's what it means. So it's up to the designer of the floating point unit to carry sufficient precision in the intermediate steps to ensure that no precision is lost, except as a result of the final rounding. So let me give you an example. When you multiply two floating point numbers, the result, so let's say the two significance are 1 point something with 23 bits of precision, okay? 23 bits of the fractional part. When you multiply two such numbers, you get twice as many fractional bits, 46 bits, okay? But 46 bits of fractional precision is not representable in IEEE standard. So at the very end, you're forced to round that value into 23 bits, okay? Now the requirements for the standard says that the only error that you're allowed to commit is in that final rounding. No additional error should be present until you do the final rounding. So here is an example. Suppose I have two floating point numbers whose significance are 1 plus 2 to the minus 1. So this is 1.1 basically in binary. And 1 plus 2 to the minus 23. That's basically a significand that has the hidden 1. That's a 1 there. And then the fractional part is basically 22 zeros followed by a 1. So both of these numbers are exactly representable in the IEEE standard, the short or single precision format. When you multiply these two, the exact product is this number. So you basically multiply the terms pairwise, you get 4 terms. 1 plus 2 to the minus 1 plus 2 to the minus 23 plus 2 to the minus 24. That 2 to the minus 24 is not representable with 23 bits of precision. Therefore, you have to get rid of it, okay? So you drop it, in other words, truncate it, or you use it to round up. Okay, so up to the first 3 terms in this expression, this is the hidden 1. So 1.1 and then 21 zeros and then a 1. That's up to there. And this is a 1 in the next position. Okay, you have to get rid of that. You can chop that, truncate it, or you can basically increment this part, round it up, and get rid of that. Okay, so that rounding, so as long as you compute this exact result in the intermediate step, then it's okay to get rid of that. That final rounding error is allowed. We have no choice, because we have to represent numbers in the number of bits that we have. So this is the chopped result, basically drop the extra bit. The error is minus 1/2 ULP, or you can round up, in which case the number becomes 1 plus 2 to the minus 1 plus 2 to the minus 22. So the last two bits, instead of being becoming 0, 1, they become 1, 0. And the error in this case is plus ULP. So the error magnitude is the same in both cases. In one case you have negative error, in the other case you have positive error. Okay, so let me talk a little bit about basic floating point algorithms, starting with addition. So here I've shown two floating point numbers, one number with significand S1 and exponent E1, the other number with significand S2 and exponent E2, and let's say E1 is greater than E2. Greater than or equal to E2. If they're equal, then that's the easy case. If they're not equal, then you have to pre-shift the number with a smaller exponent by E1 minus E2 bits. So if the difference between E1 and E2 is 1 bit, you pre-shift this number with the smaller exponent by 1 bit to the right, basically dividing it by a power of b, and then making its exponent equal to the larger exponent E1. And then when the two exponents are equal, then you take that to be the exponent of the result, and the significand of the result is given by this expression. Significand of the first number with the larger exponent, plus or minus, these are dependent on the signs of the two numbers. The significand of the second number, right shifted by the difference between E1 and E2. This will become clear with an example. So suppose X and Y are these two numbers. I'm taking, this is the hidden one, and I'm taking 8 fractional bits to make the example small enough to be able to, fit on the slide. So X has exponent 5, Y has exponent 1, and these are the significants. The number with the smaller exponent be right shifted by the difference between the two exponents, which is 5 minus 1, 4. So Y is right shifted by 4 bits. So the one that was here goes 1, 2, 3, 4. Will sit there. Okay. So it will get 4 extra bits. So in the intermediate results, we have to keep these 4 bits because they may come in handy later. Now the exponents are both 5. So the result will be to the 5. And the sum of these two numbers will be this number, which has 4 extra bits that we need to get rid of in the final rounding. And because this is 1/2 ULP, this is 1/4 ULP, so collectively this is a value greater than 1/2 ULP, we round up. We add 1 to this position, which changes these two ones to zeros and this 0 to 1, and that's the rounded sum. Of course, in this example, I was lucky that the sum of these two numbers was 1 point something. In general, because this is 1 point something, this may also be 1 point something, or at least can be 0.1 something. When you add these two, the result may exceed 2. And therefore, you will have 2 whole bits here. And then you need also an adjustment to get rid of the extra whole bit by shifting to the right. And that's known as normalization. So in general, for addition, you need normalization when the result exceeds 2, equals or exceeds 2. And then once you have done your normalization, you have to round to get rid of the extra bits. Multiplication is actually conceptually simpler. So here, two floating point numbers are being multiplied. Basically, to multiply two floating point numbers, we add the exponents and multiply the significance. Of course, multiply the signs too, XOR the signs. So if both of these are positive, the result will be positive. If both are negative, the result will be positive. If one is positive, the other one is negative, the result will be negative. So you XOR the signs, multiply the significance, and add the exponents. When you do this, because each of the significance S1 and S2 is in the range 1 to 2, the product will be in the range 1 to 4. Therefore, you may need a post-shifting to get rid of that value that is too large. So basically, you can say that range 1 to 4, you can divide it into two subranges, 1 to 2, which is a valid subrange, and then 2 to 4, which is too large by a factor of 2. So you do a right shift in that case, and when you do a right shift in the exponent, in the significand, you increase the exponent by 1 to compensate for that. Division is similar. So two numbers being divided, you divide the significance and subtract the exponent. Again, a similar thing can happen here. Each of these numbers in the range 1 to 2. So the range of the ratio of these two will be 0.5 to 2. This is an open interval. It cannot be 0.5 and it cannot be 2. So again, I can divide this range into two subranges, 0.5 to 1 and 1 to 2. The 1 to 2 part is already in the proper range for the standard format. 0.5 to 1 is too small by a factor of 2. So I multiply the significand by 2 by left shifting it and then subtract 1 from the exponent. For square rooting, which as I mentioned is considered a basic operation, we distinguish two cases. If the exponent e is even, then the square root of this floating point number is the square root of s times b to the power e over 2. E being even, this is an integer, and therefore we are done. So basically, the square rooting problem is converted to extracting the square root of the significand, which is a fixed point number. If e is odd, then we multiply the significand by b and subtract 1 from the exponent. So this is the same number still. And then we extract the square root of b times s, and e minus 1 is now even. We divide it by 2. So putting these two cases together, we either extract the square root of the significand or the square root of twice the significand in the case of IEEE binary standard. B is equal to 2. Okay, and therefore this S star, the number for which we need to extract the square root, is in the range 1 to 4. If you don't double it, in this case, it's in the range 1 to 2. If you double it, it's in the range 2 to 4. Therefore, we have to be prepared to extract the square root of a number in the range 1 to 4. Now, interestingly, the square root of the number in the range 1 to 4 will be in the range 1 to 2, so no post adjustment is needed in this case. So you directly extract the square root of the number that is in the range 1 to 4, and you get a number in the range 1 to 2, which is the proper significand for the result. So square rooting requires this pre-processing step to look at the exponent. If it's even, leave S alone. If it's odd, subtract 1 from the exponent and double S. Then extract the square root of S star, this modified S, and then divide the exponent or modified exponent by 2. And dividing by 2 is simply right shift, so it's pretty easy. Okay, overflow or underflow is impossible in this case, and no post-normalization is needed. Now the IEEE standard 754, both the 2008 version and the newer 2019 version, define 5 rounding modes. Of course, there are some conversions from fixed to floating point. These are all defined in the standard. Between floating point formats, like how do you convert a short format to long format and vice versa. So conversion from higher precision to lower precision is rounding. And there are 5 rounding modes that are defined. Round to nearest ties away from 0. Round to nearest ties to even. This is basically the tie-breaking rule. I'll talk about this in a minute. That's the default rounding mode. So round to nearest ties to even is the default rounding mode. Round towards 0, or inward rounding. Round toward plus infinity, upward rounding. And round toward minus infinity, downward rounding. So before talking about rounding, there are some exceptions that are defined in the standard. And these exceptions are divide by 0, overflow, underflow. Inexact result is also a type of exception. When you have 2 exact values, but you do an arithmetic operation on them, and the result is inexact, you may want to know about the result being inexact. There are a bunch of invalid operations. So, for example, in addition, if you add plus infinity to minus infinity, the result is undefined. If you multiply 0 by infinity, remember that 0 is often a surrogate for a very small number. Remember when we have underflow, we flush something to 0, or it may be true 0. Okay, so you can't tell by looking at this 0 whether it is an inexact 0, something that was rounded to 0, or a true 0, mathematical 0. Infinity similarly can be a number that was too large, so we chose to represent it as infinity. It's not a true infinity. So this result is undefined because we don't know enough. So for example, if this is true 0, and this was a number that was too large and was rounded to infinity, you may argue that this product is 0, but you don't know about that, okay? Dividing 0 by 0 is undefined, and infinity by infinity. And in square rooting, when a number is less than 0, it's negative. its square root is undefined, so that's an invalid operation. And these invalid operations produce nan as the results. So that nan is basically a flag that sits there, and when you encounter a number that is nan, that's a signal to you that something has gone wrong in the course of the computation and you got an undefined value. Okay, rounding basically means getting rid of extra digits or bits of precision. It's easier, more intuitive if we talk about rounding a number to integer. We don't have to round to integer. We can round to fewer bits of precision. But let's say I have a number with a bunch of whole bits and a bunch of fractional bits, and I want to get rid of the fractional bits to generate an integer. Okay, so this y integer is the rounded version of this number. The simplest rounding scheme is just chopping. When you chop these fractional bits, or the bits that you're trying to get rid of, the bits of y will be exactly the same as x. Okay, so when you chop, you simply ignore those extra bits, and you keep the remaining bits. But in general, these bits will not be the same as those bits of x. So I have a sequence of diagrams that sort of graphically depict these various rounding schemes that we will discuss. Truncation or chopping is represented by this diagram. So what you see on this diagram is the value of x on the horizontal axis and chop of x, basically the truncated version of x. Okay, whenever x is in the range 0 to 1, not equal 1, but just less than 1, it's chopped to 0. If it's 1 all the way up to, but not including 2, it is chopped to 1. 2 to 3 is chopped to 2, and so on. So these red lines represent the value of chop of x, the function chop of x as a function of x. And these heavy dots basically resolve the ambiguity, because on this vertical line there's a point here and there's a point here. That heavy dot says we take this value. So if the value is 1, we chop it to 1. If it's just below 1, okay, we chop it to 0. So you see that the error in chopping can be up to almost 1 unit. When you have a number that is just below 2, almost equal to 2, and you chop it to 1, you commit 1 unit of error, almost 1 unit of error. Okay, so this is for sign and magnitude values. When you chop, numbers in the range 1 to 2 become 1. Numbers in the range -1 to -2 become -1. If you have 2's complement representation, then what happens, because the bits that you chop are positively weighted, the number always goes down in magnitude. So if it's positive, it goes down when you chop. If it's negative, it also goes down. So numbers in the range -1 to 2 becomes -1 to -2 become -2 when you chop those extra bits. Okay, so for 2's complement numbers, chop of x is the same as downward directed rounding. We always round downward, okay, towards smaller values. Whereas here, in the case of negative numbers, we chop upwards, we round upwards. So remember that for 2's complement numbers, chopping always reduces the magnitude of the number, whether it's positive or negative. So this is the rounding scheme we are used to in manual calculations. It's round to nearest. So when we have a value such as 1.3, we round this to the nearest integer, which happens to be 1. If you have 1.8, you round it to 2. Now for midpoints, so 1.5, you have two options, round it down and round it up, and the error will be the same in both cases. And by convention, we choose to round those halfway values up. Okay, so 1.5 becomes 2, it doesn't become 1. Negative 1.5 becomes negative 2. Okay, not negative 1. So this is the standard way that we use rounding in manual calculations. This reduces the maximum error by a factor of 2. Instead of the maximum error being 1, almost 1, it becomes 1/2. Okay, so it's better with respect to the worst case error, and therefore error accumulation tends to be less of a problem with rounding. However, this rounding scheme that we are used to and use manually has this slight disadvantage. So suppose I'm trying to round a number that has 2 fractional bits. Okay, so there are a bunch of whole bits and 2 fractional bits that I'm trying to get rid of. When those 2 fractional bits are 0, then I round down. Basically, I ignore those zeros and commit no error. Because those bits that I got rid of are zeros, there's no error. If those bits are 0, 1, then I chop and commit an error of 1/4. Okay, remember we have ULP in this position. This is 1/2 ULP. This is 1/4 ULP. An error that is minus 0.25 ULP. If the two bits are 1, 1, then I round up, committing an error of 0.25. And the midway point, I mentioned by convention we round up, and therefore we commit an error of 0.5. If you average out these errors, assume that these 4 cases occur with equal probability, then you have this slight upward bias of the error. The average error is not 0, but it's 0.125. And therefore, over the course of long computations, the errors are biased. Okay, they don't cancel each other out, but you always go up in values because of that bias. It would be nice if we did not have that bias. Okay, round to nearest even tries to remove this problem by alternating between rounding up and rounding down. So if I have 1.5, I round it to 2, to the nearest even number and the midway point. If I have 2.5, I round it down to 2. Okay, so some midway points are rounded up, some midway points are rounded down, and there are an equal number of such points, and therefore over the course of long computations, errors tend to cancel each other out. There's no guarantee, of course. The worst case error is still the same, but unless we are unlucky, these errors tend to cancel each other out. And this is why round to nearest even is the default rounding mode in IEEE standard, because it has this desirable properties of error being symmetric. Some midway points are rounded up and some midway points are rounded down. Okay, this is a rounding scheme on the right of the slide called R-star rounding, or rounding to the nearest odd number. Just for symmetry, I wanted you to see that this rounding mode exists. It's not used much in practice. We use round to nearest even. And the reason that round to nearest even is better than round to nearest odd is that when you get to even, basically when you have 2 instead of 3, the least significant bit is 0. And therefore future computations that lead to right shift are less likely to produce errors, because 2 divided by 2 is 1 with no error, whereas 3 divided by 2 is 1.5, and then you commit an error after a right shift. So even numbers are less likely to produce subsequent errors as a result of shifting. Okay, it's the simplest symmetric rounding scheme is basically chop the extra bits and force the least significant bit of the result to 1. A normal chopping basically leaves the least significant bit as it was before, doesn't change it, it just drops the extra bit. In this rounding scheme, we chop and force the least significant bit to 1. And this is basically the graphical representation of this rounding scheme. So numbers in the range 1 to 2 are chopped to 1. Numbers in the range 2 to 3, you chop and then force the least significant bit to 1, go to 3. So you see that some values are rounded down, some values are rounded up, and therefore there is some symmetry. This is called jamming, this rounding mode. It's a very simple rounding scheme to implement, but its error is as bad as regular chopping. It can be up to 1 unit. This one I'm going to skip. It's not used anymore. It's called rum rounding. Basically, it's an attempt to prevent carry propagation when you round a number up. In the worst case, when you round up, carries can propagate all the way to the end of the number, therefore making the rounding slow. This one basically uses a ROM to decide what the rounded, the few least significant bits of the rounded value are read out from a table. Okay, it's a pretty weird error characteristics. In some cases, the error is large. In some cases, the error is just like rounding. So the hope is that these values that have large errors do not occur too often to cause problems. Okay, in IEEE 754 standard, we also have directed rounding modes. Directed rounding means that the rounded value is always upward, goes up or goes down. And this rounding mode is useful when you're trying to compute the upper bound for something. Okay, it's good to round up, because when you round something up, that value, rounded value, is still a valid upper bound. Whereas if you round it down, there's a danger that the value obtained is no longer a valid upper bound. Similarly for lower bound. When we talk about interval arithmetic, in the lecture after the next one, you'll see that these directed rounding modes are quite useful for interval arithmetic. So this is a visual representation of directed rounding. Upward rounding, see the value, rounded value is always above, at or above the exact value. Downward rounding, the rounded value is always at or below the value being rounded. Okay, in this last section of the chapter, talk about another way of representing real numbers called logarithmic number representation. So basically, a logarithmic number representation, you can view it as the extreme of a floating point representation, in which the significand is always 1. It doesn't have any fractional bits. So all we have is the exponent. So to represent a logarithmic number, we represent its sign, and the exponent. So this is why it's also called the sine and logarithm number system. This is the sign of the number. This is the base b logarithm of the number. Okay, so e, the exponent, is the base b log of the magnitude of x. Okay, the sign is already represented there. Of course, unlike floating point, this e, it doesn't make sense to restrict e to be an integer, because if e is an integer, we only can represent a limited set of numbers. Well, let's say the exponent is 2. If e is limited to be an integer, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. So I can only represent numbers 0, 1, 2, 4, 8, 16. That's not very useful. Therefore, e is taken to be a fixed point number with whole bits and fractional bits. And this radix point is implied. Okay, it's at a particular position within this field E. So this is the meaning of logarithmic number system. It has a sign and it has a fixed point representation of the logarithm of x. And this base b, you can choose anything you want. Usually we choose it to be 2. So base 2 logarithm of x. Okay, so here are some properties of logarithmic representation. The logarithm is often represented as a 2's complement number because the logarithm can be negative or positive. So a logarithmic number has 2 components, the sine of x and the logarithm of x. So sine of x and log base 2 of the magnitude of x. Okay, why are we interested in this number system? One of the primary motivating factors is that multiplication and division become extremely simple because log of the product of x and y is log of x plus log of y. So to multiply two numbers, because we represent the two numbers as logarithms, you just add those two logarithms and you get the representation of the products. So multiplication is converted to addition, which is a much simpler operation. Similarly, division is converted to subtraction. Okay, this advantage doesn't come for free because now addition and subtraction become more difficult. Okay, we'll talk about this later. So here's an example of a 12-bit base 2 logarithmic number system. There's a sign bit. I've chosen to have 5 whole bits and 6 fractional bits. And this particular bit string, this particular number, represents, first of all, it's negative, to the power this number, you see it's, let's see, it's a 2's complement number. So it's -8, sorry, -16 plus 4, -16 plus 4 plus 2, so that's -10. And then to that -10, I also have to add these, which is 1/8 plus 1/32 plus 1/64. The result will be this. So this is to the power -9.828125, which is basically the decimal equivalent of this 2's complement number. Okay, and that's this number. It represents this number in radix 10. 11/10,000, -11/10,000 is that number. The number range is, for this particular format, is approximately -2^16 to 2^16, because the largest number that I can represent, okay, this is 0 because I'm positive. I have 1, 1, 1, 1, that's 15. 1, 1, 1, 1, 1, that's almost 16. And then on the negative side, this will be 1, so that goes to -2^16. So this is roughly equivalent to 17-bit integer format in terms of range. But notice that it has a lot of precision. It doesn't just represent integers. So how does it do it? Well, there's a trade-off. For larger numbers, the spacing between numbers increases. So here's a chart that I showed you early in the course to show you that if you have 16 tokens, a 4-bit representation, it's up to you how you use those 16 tokens to represent 16 values. And among those, we talked about logarithmic representation, in which we use these 4 bits, let's say this toy example, 2 whole bits and 2 fractional bits. And this is unsigned. I'm not bothering with sign in this particular format. Okay, so numbers go from near 0 to about 12. So you see it has a pretty wide range, almost equal to this integer format. But it has a lot of precision for small numbers, where we do need that precision. We need more precision for small numbers. Okay, so like floating point numbers, this provides both high precision for small numbers and wide range so that we can represent large numbers. One advantage compared to floating point is that this distribution is pretty much uniform. So if you compute the relative error for numbers in this range, in this range, in this range, they're all about the same. Whereas in floating point, that value changes because of those tick marks that I showed you in an early diagram in this chapter. The tick marks have wide spacing for a while, then they become smaller, then smaller. That variation is not smooth, okay? It jumps from one spacing to the next spacing. Whereas here the variation is smooth, and therefore the error can be tends to be pretty uniform in the entire range of representation. Okay, we'll get back to this at the end of the next chapter, the next lecture, when we see how arithmetic operations, including addition and subtraction that I skipped, are implemented in this logarithmic number system, and also, on floating point representation. So in the next chapter, floating point operations, we deal with both algorithms for floating point operations and algorithms for computation with logarithmic numbers. That's all for this chapter. I'll see you in the next lecture. Bye.